structure provides a brief conceptual description of exploratory factor analysis. We will discuss the purposes of factor analysis, the difference between exploratory and confirmatory factor analysis, as well as the difference between component analysis and common factor analysis. I will describe different methods of factor extraction or estimation methods, as well as procedures for determining the optimal number of factors. I will explain the concept of factor rotation and how factors should be named. Finally, I will explain what factor scores are and the purpose of estimating factor scores. First of all, we should discuss what factor analysis is. Factor analysis is a general term that covers a set of multivariate procedures that investigate the structure of interrelationships or correlations among variables, and it identifies groups of variables or groups of items that share some commonalities. These groups are underlying dimensions of the data, also known as factors. They may represent different characteristics or components of a certain construct. For instance, if we measure intelligence, we may identify different dimensions of intelligence: a verbal component, a mathematical component, a spatial component, and so on. EFA is used when researchers are not certain about the number of dimensions that may be underlying the data, or as a data reduction method, and I will explain what data reduction is on the next slide. With this approach, the researcher does not have a hypothesis. He or she is exploring the relationships among variables to identify patterns. Therefore, the number of factors or components to be estimated is not specified from the beginning. It is determined later based on what the data are showing. Confirmatory factor analysis, or CFA, as the name implies, is a procedure that continues a line of research and relies heavily on theory and prior findings. In this case, the researcher has preconceived thoughts about the number of dimensions that should underlie the data and which items are measuring each one of these dimensions. Therefore, the number of factors is specified beforehand, and the purpose of the analysis is to test the hypothesis, or to determine the extent to which the new data fits the expected structure. In this presentation, I will focus only on exploratory factor analysis. The main applications of factor analytic techniques are data reduction, or the identification of an underlying structure of the data. Data reduction can be obtained by calculating, for each component or group of items, an overall score, a composite measure that retains as much information from the original variables as possible. Therefore, all the variables included in one factor are replaced by a single variable. For instance, we can use this procedure to create an overall score for a section of a survey or a test. Another way to reduce the dimensions of the data is to select from each component the most representative items and eliminate the items that provide redundant information. EFA can also be used to identify groups of items that share something in common. Items are assigned to or classified into a certain group because they provide similar responses. For instance, an IQ test includes a multitude of items that ask respondents to complete a wide variety of tasks. Factor analysis of the results will reveal that certain groups of items are providing similar results based on the type of task involved. We typically see that, for instance, items measuring verbal skills are assigned to a group, whereas items that are measuring computation skills are assigned to a different group. These groupings are based only on the patterns of responses, regardless of what the researcher intends to measure with these items or how they're grouped in the measurement instrument. The results reflect patterns of variation in the data and are therefore data-driven. It is up to the researcher to then determine the extent to which these results make theoretical sense. EFA implies a sequence of steps. These steps also require the researcher to make some decisions. The first step is to select the variables for exploratory factor analysis. These are all the variables in the measurement instrument that are assessing the overarching construct or the topic that we are investigating. For instance, if we are exploring factors of intelligence, we are including all the items on an IQ test that we think are measures of intelligence. Similarly, if we're investigating factors related to motivation, we should include all the items on the motivation scale that we believe are measures of these factors. Be careful only to include the variables that are measures of the constructs investigated, and no other variable that may be available in the dataset, such as demographics or other information. An important issue that we should discuss here is the issue of sample size. Different authors propose different rules of thumb, but the minimal requirements are to have a sample of at least 50, but preferably larger than 100 cases, and at least 5 observations per variable. For instance, if we have 20 variables, we should have data from at least 100 individuals. The next step is to compute correlations between the variables included. This is a correlation matrix, so for each variable we compute the correlation with every other variable. The next step is extracting or identifying the dimensions in the data. In other words, identifying the groups of similar items or the factor structure. Fourth step is the factor rotation, which consists of a series of computation procedures aiming to optimize the factor solution, and finally the interpretation of the factor solution. Of course, we use statistical software for all the computations, but it is important to understand the meaning or the purpose of each procedure. The critical assumptions for exploratory factor analysis are more conceptual than statistical. When checking whether assumptions are met, we should consider issues such as the distribution of the data or the degree to which data are multivariate normal, as well as the extent to which variables are correlated. A moderate degree of multicollinearity is desirable, but higher degrees of multicollinearity may induce estimation bias. It is also assumed that the relationships among variables are linear. The most frequently used estimation methods are also based on the assumption that variables are continuous. However, there are estimation methods that can be used with ordinal data. There are also methods that can be used with non-normal data, so the nature of the data is not stopping us from conducting factor analysis, but is very important to consider in order to choose the appropriate estimation procedure. To ensure that the data matrix has sufficient correlations to conduct factor analysis, we can just visually explore the correlation matrix. If the visual inspection shows that very few variables have correlations above 0.3, then factor analysis is probably inappropriate. At the same time, as I mentioned before, having many correlations above 0.7 may induce estimation bias. Correlations between variables can also be analyzed by calculating partial correlations among variables. That is, the correlation between variables when the effects of other variables are taken into account and partialed out. If factors are truly underlying the data, then partial correlations should be small because the variable is explained by the factors. The anti-image correlation matrix is the negative value of the partial correlations and can be obtained in SAS or SPSS. When partial correlations or the anti-image correlations are large, the matrix is not suitable for factor analysis. The Bartlett test of sphericity is a statistical test for the presence of correlations among variables and provides the statistical probability that the correlate matrix has significant correlations among at least some of the variables. Another measure for investigating intercorrelations among variables is the measure of sampling adequacy, or MSA. This is an index that ranges from 0 to 1, where values closer to 1 indicate less error in predicting one variable based on the other variables. For this index, values below 0.5 are considered unacceptable. Values around 0.6 are mediocre, values around 0.7 are acceptable, and values 0.8 or above are considered very good. Selecting an extraction procedure or an estimation method depends on the purpose for which EFA is conducted, whether it is component analysis or common factor analysis. But before we explain the difference between the two, we have to discuss the concept of variance. Each variable has a certain variance, which we know is the square of its standard deviation. The variance of a variable can be attributed or divided into three different sources. The common variance is the variance that a variable shares with the other variables in the dataset. The specific variance, or the uniqueness, is the variance that is only characteristic for a particular variable. And third, we have the error variance, which is the variability that is introduced in the data gathering process due to measurement error. The major distinction between principal component analysis and common factor analysis is the type of variance that is used in the computation process. We already know that factor analysis is an investigation of relationships among variables and tries to determine the extent to which these variables vary in the same way. Principal component analysis uses the total variance of the variables in the computation process, whereas common factor analysis uses only the shared or the common variance for computation. Principal component analysis has the advantage of maximizing the variance extracted. This procedure is used mostly for measurement or data reduction purposes and when prior knowledge suggests very little error variance. Its purpose is to identify the components of a dataset or the scales of an instrument without assuming that these components or groups of items are measuring a latent construct because the unique and error variances are not removed. The identified components are simply linear combinations of a group of variables that retain as much information from the original variables as possible. Therefore, although principal component analysis is often referred to as factor analysis, it is not really an analysis of factors. Common factor analysis is used to identify latent dimensions of a construct. The term latent is used because the unique and error variances are parceled out, and coefficients are estimated based only on the shared variance. Latent variables are variables that are not observed directly. They are called latent or underlying dimensions because their features are inferred based on the patterns of variation in the data after removing the variance due to measurement error. After selecting the variables that we want to include in the analysis, we have to decide which estimation or extraction method to use. Selecting an estimation method depends on the purpose of our analysis as well as on the nature of the data we are working with. For instance, the principal components method is used for data reduction purposes. For common factor analysis, we can choose methods such as maximum likelihood or principal axis factoring. The maximum likelihood method has the advantage of extracting the maximum amount of variance, but is based on the assumption of multivariate normality and assumes continuous variables. When these assumptions are not met, we can choose other methods, such as principal axis factoring. Depending on the statistical software we're using, we can also use the diagonally weighted least squares method, unilateral, the mean and variance adjusted weighted least squares method in M+, or the Bayes estimation method also in M+. This is just an introduction to this topic. If you're conducting a study, I strongly recommend considering the advantages and disadvantages of the different estimation methods available in each software in order to the best decision for your research scenario. After factors are estimated, the factor solution is rotated. The goal of rotation is to simplify and clarify the data structure. The term rotation means exactly what it implies, that the reference axis for the factors is rotated around the origin until another solution is reached. There are two types of rotation methods. One type is represented by the orthogonal methods, which are employed when the factors are not correlated. This is rarely the case in social sciences, so we most often use the oblique rotation methods, which are more appropriate for correlated factors. There are many types of rotation methods in each category, and depending on the statistical software that we're using, when choosing the rotation method, we have to consider the advantages and disadvantages of each method and decide which one better serves our purpose. Again, this is just a brief introduction to EFA, so please refer to the literature to learn more information about these procedures. To illustrate how to make decisions while conducting EFA, I will use a fictional dataset available in the factor analysis literature. This is a set of items from the Statistics Anxiety Questionnaire. I will use these items for factor analysis to identify different dimensions of statistics anxiety. In exploratory factor analysis, we specify all the variables that we want to use for analysis, in our case the items of the SAQ, and after running the analysis, we have to decide how many factors are underlying the data. There are a set of criteria that we can use to make this decision. One criterion is the number of eigenvalues larger than 1. The EFA output includes a table that lists all the factors that could be identified and the amount of variance explained by each one. Our data includes 23 items, so theoretically, the number of factors can range from 1, this would be the situation in which all items would measure a single factor, to 23, where each item is a separate factor, which doesn't make much sense for us because our purpose is to classify items into groups, which should include at least 3 items to be considered a factor. We can see in this table that the first 4 factors have eigenvalues larger than 1. Therefore, this criterion suggests a 4-factor solution. Another criterion used to decide on the number of factors is the percentage of variance explained by the factor solution. We can see in this table the amount of variance explained by each factor, as well as the total or cumulative amount of variance explained by all factors. With the 4-factor solution, the total variance explained is, in our case, about 1%. In social sciences, it is ideal to have values above 60%, but lower values are sometimes considered acceptable. The scree test is another criterion used to determine the number of factors, which consists of plotting the eigenvalues against the number of factors. The point at which the curve begins to straighten out, or the elbow of the curve, is considered to indicate the maximum number of factors to extract. In our case, the scree plot suggests that 3 or 4 factors should be extracted. Another criterion, and I would say the most important one, is the interpretability of the factors. Solutions with different numbers of factors should be examined, and the item grouping that makes most sense from a theoretical point of view should be selected. In our case, we should probably compare the solution with 3, 4, and 5 factors. Based on the number of eigenvalues larger than 1, I started with the 4-factor solution represented in this table. The numbers listed in the 4 columns are the item loadings. For each item, we compute a coefficient that shows the correlation between that item and the factors. The item is assigned to the factor with the highest loading. For instance, the first item is assigned to the first factor, the second and the third items are assigned to the fourth factor, and so on. After determining to which factor is each item assigned to, we have to analyze the items in each factor and determine whether they have something in common or if they're all assessing a distinct dimension. For instance, all the items in the first factor are related to the fear of statistics in general or different topics in statistics. Items in the second factor all refer to the fear of computers and software. Items in the third factor are referring to the fear of math, whereas items in the fourth factor refer to peer comparisons. Therefore, we can say that the concept of statistics anxiety has 4 latent dimensions or 4 factors: fear of statistics, fear of technology, fear of math, and peer comparisons. These will be the names of the 4 factors. To optimize the factor solution, we should eliminate the items that are cross-loading or have high correlations with more than one factor. In this example, we do not have cross-loadings, but it means that one item has 2 or more loadings that are above 0.3. We should also exclude the items that have low loadings below 0.3 on all items. In this example, item 15, computers are out to get me, has low loadings on all factors and should be eliminated. Items should be deleted sequentially, beginning with the worst offender. Because EFA is a multivariate procedure, deleting one item changes the coefficients for all the other items, and we may realize that other deletions may no longer be necessary, or that additional deletions are needed. Deletions should be made until we obtain a simple structure, which means that every item clearly loads under a single factor. They have high loadings for one factor and very low loadings for the other factors. For example, I selected the 4-factor solution as the optimal or the final solution. I used maximum likelihood as the estimation method with pro-max rotation. After deleting 3 items, I obtained a simple structure. This is an example of how to report the final factor solution. Notice that after making these changes, some of the loadings have increased, indicating that the data has a more clear structure now. Remember that after deleting items, we should not have factors with less than 3 items. I reorganized the table to make it easier to read. Items from the same factors were grouped together and ordered in the descending order of their loadings. Items with the highest loadings in a factor are also called marker items, and they're listed first. These are the best indicators of that factor and are also often used to name the factor. Notice that the loadings for the other factors, which were not significant, have been deleted to increase readability. When reporting the results, we should also include the factor correlations. We can see that factor correlations here range between negative 0.1 and 0.67. The strongest correlation is between the fear of stats and the fear of technology. Interestingly, the 4th factor is negatively correlated with the other factors, but because these data are simulated, I will not spend much time discussing any of these correlations. The purpose of this presentation is just to illustrate how to report and to interpret the results. Many times, after obtaining a factor solution, researchers need to find a way to relate the results of factor analysis, which is a variable-oriented analysis, to the individuals included in the data set. In other words, we often need to know how does a particular individual or a group of individuals relate to the identified factors. The computation of factor scores allows us to do this. Factor scores are estimates that show us where each individual is located on the identified factors, or how much of each factor is present in each individual. For instance, for one individual in our dataset, we may obtain scores such as the ones presented on this slide. If these scores have a mean of 0 and a standard deviation of 1, we can see that this individual has scores that are very low on fear of statistics and technology, but has significant fear of math, and is somewhere close to average on peer comparisons. These scores can then be used for further analysis, such as group comparisons, analysis of variance, cluster analysis, regression analysis, and so on. There are several different ways to compute factor scores. There are two main categories of computation procedures: the non-refined methods and the refined methods, which are a little more complex. Each procedure has advantages and disadvantages and is more appropriate for some research scenarios than others. Please refer to literature for more details on the computation procedures. This presentation provided a conceptual explanation of exploratory factor analysis. We discussed the purposes for which this analysis is conducted, the differences between exploratory and confirmatory factor analysis, as well as the difference between component analysis and common factor analysis. We have also described some methods of extracting and rotating factors and showed the criteria for selecting a factor solution. Finally, we defined factor scores and explained how they can be used for further analysis. This was a very brief introduction to EFA. For more details on the topic and information on computation procedures, please refer to the EFA literature.